Okay, well, we'll begin with a couple of announcements. Homework 10 is due on Wednesday, 2 days from now. And we're also going to have our exam 2 days from now, which means I need to write the exam. It's open book, open note. You can use your previously solved homework, your previously solved examples. You can use those as a reference or, as a starting point, but you have to solve your work individually. And so the exam should reflect what you yourself have done. And so you shouldn't use any outside websites. The only website that you should access during the exam is Blackboard. You shouldn't communicate with other people during the exam. Essentially, you know what cheating is, and I know what cheating is, and you shouldn't cheat during the test. It should be a reflection of what you know and understand. The exam will open at 12:30 and will stay open until 2:30. And so that gives you 2 hours to take the test. And you need to upload your scanned copy of hand calculations as well as Excel if there is an Excel problem. Both of those things should be uploaded to Blackboard before the deadline. I had an exam with my engineering economy class on Friday. I was a little bit surprised at how many people had trouble uploading their files before the deadline. There were a couple of people who emailed it to me after the deadline, and the disadvantage with that is that then I'm not able to provide the same detailed feedback as I can, and it's a little bit more tricky to keep track of everything because email is a place where garbage goes, right? Everything I get via email, it's garbage. Just spam, people asking me for things. It's usually like the important things come to me different ways. So you're important, so submit it the way that important things are submitted through Blackboard. All right. Project Phase 3, reservoir sizing. We went through a demo last week where I showed you the spreadsheet technique you need to size the reservoir. So if you would like to watch that video again just to refresh your memory of what the process is, it's the sort of thing where you can finish that phase of the project really easily, quickly. For the draft submission that's due on the 12th, you do not have to include a write-up. The final submission at the very end should have a written section of the report that discusses the methods used for every phase of the project. So that's to say, in phase 1, draft submission for demand estimation, you were supposed to have a write-up during that phase to help me understand what your assumptions and calculations were about. Most of you did that. Some people didn't have that written commentary with phase 1, and it absolutely should be there for the final submission. But the final submission at the end of the semester should also have write-ups related to the pipe sizing, so describing your optimization method. It should have a section 3 where you talk about the sizing of the reservoir. It should have a discussion about the cost of the network and so on. But during this draft phase, all I need is your spreadsheet. So are there any questions related to the announcements? Okay. Well, let's talk about spillways and weirs today. We are very fortunate to live alongside the Ohio River. One of the things that makes America a very productive and rich nation is the series of waterways that we have running through the country. There's the Missouri River and the Mississippi River, and both of those are navigable, meaning that very heavy cargo can be moved at very low cost up and down those river systems. Along the east coast of the United States, we have the Intercoastal Waterway. There are excellent ports along the coast of Texas as well, the Gulf of Mexico. And then in the northwest part of the United States, there's a series of navigable rivers there as well. You can see kind of the watershed that feeds into that network. And so barge traffic can go through Idaho, which is a landlocked state, but it happens to be agriculturally really productive. There's quite a lot of sugar beet and potato, and It's a productive agricultural region, and it's very inexpensive to move equipment and materials. Like, they use a lot of fertilizer, unfortunately, in Idaho. When you're growing crops in volcanic soil that's not nutrient rich, it requires a lot of phosphorus and nitrogen to make that happen. So they bring in some of that heavy bulk stuff via barge, and it's a lot less expensive than it would be if those things were brought in by rail or certainly by truck. So that's one of the things, when you think about why is America rich, you wouldn't necessarily think that it's because of its rivers, but there's, I think, a really compelling argument that that's part of it. And so keeping those rivers navigable is one of the tasks that hydraulic engineers have. And so making sure that the elevation of the water can be controlled and is at an elevation that, on the one hand, doesn't flood surrounding areas, but then on the other hand is deep enough so that barge traffic, heavily laden vessels, can go up and down without scraping the bottom, without being too high so that it's running into bridges. So we need ways to control the flow. The Grand Coulee Dam, which dams the Columbia River, has a multitude of really beneficial uses. On the one hand, it's excellent for flood control. So they have the capacity to kind of smooth out the peak flows that would come during periods of wet weather. They can retain that extra water behind the dam so that communities downstream of the dam that otherwise would have maybe be threatened by highly variable flows don't experience that same damage. So it has flood control benefits. It also generates electricity, which is really valuable. They say that much of the Pacific Northwest benefits from hydropower. The cities of Portland and Seattle, I think both get a big fraction of their electricity from hydropower. And then another function of the Grand Coulee Dam is to control the elevation of the water upstream. So the water that comes down the front face of that dam picks up a lot of speed. It's a tall dam. I maybe should have looked that up so I could put the statistic on here. But the flow down the front spillway of the dam, when the spillway is operational, means that the flow is going supercritical down that steep slope. And we're going to talk, starting next week, I think, about hydraulic jumps. And hydraulic jumps are when you have supercritical flow that transitions to subcritical flow. Thanks, Luke. 1483. I wonder if that's the elevation above sea level. That may not be its height from the base of the dam to the top of the dam. That would be spectacularly tall if that was the net height of the dam. I'm guessing that's probably its elevation above sea level. Logan says 550 feet from top to bottom. Thanks for looking that up. That's still pretty dang tall, though. 550 feet. So we have to really understand a lot about what the flow is doing when it comes down the front face of the spillway. It's going to be moving at a fast velocity. And one of the things that Bernoulli's equation tells us about high velocity is that it can come with localized low pressure. And this is more of an issue in enclosed conduits, where there's a penstock or a pipe that has the water from a dam going through the pipe and discharging to the river below. If the water is moving really fast through that pipe, there can be locations where the pressure drops below the vapor pressure and there can be cavitation. But there can also be some scour and erosive effects on the front face of a dam. And so that's why they'll really go to quite great lengths to make sure that this dam is smooth, well-armored concrete that's going to stand up to spillway flows when they occur. So let's talk a little bit about the equations we can use to understand how much water comes over a spillway. And a spillway can be modeled as a sharp-crested weir. It's not actually a sharp-crested weir, but we have a way of conceiving of it. When I say modeled, that means, a model may be a physical representation of something, like a toy car that's a a representation of a full-size prototype. So that can be one kind of model. Another kind of model, though, could be just an equation or a formula that relates two different things. It may relate, for example, flow rate and the elevation of water over a spillway. And so this is the model for flow rate over an overflow spillway when we assume that it's behaving like a sharp-crested weir. And so this shaded area is actually matched into the rest of the dam. It's just, this formula is derived from us understanding it. It kind of behaves like a sharp-crested weir, and that when the water is going down the front face of the spillway, that there's no further resistance, that the spillway part of this isn't inhibiting the free flow of the water over the edge. So that's the way that it is like a sharp-crested weir, because when water goes over the edge of a sharp-crested weir, then it's no longer backing up flow at all. So we definitely have non-uniform flow. Think about the different flow type classifications we've talked about last semester in this. Non-uniform means that as you move in the direction of flow, some aspect of that flow is changing with respect to position. So that can be velocity, that could be its depth, and here we do see that the water begins to draw down as it approaches the spillway. There's some dimensions that are provided here, and note that the H that we have in a typical equation for a sharp-crested weir, H would be referring to the height above the sharp-crested weir to the water level upstream before this drawdown occurs. So we're not measuring H immediately above the sharp-crested weir. We're measuring it far enough upstream that the drawdown hasn't yet begun. So that's one key thing that I want to mention about H. But then the other key thing is that the physical height of the spillway, so it's concrete all the way. So concrete, there's still a little bit more vertical elevation, but we say that the sharp-crested weir ends where the curvature begins. And so this gap height is 0.11 H, and then the overall H is 0.11 H plus HD. And this is confusing a little bit, but we're saying H equals HD plus 0.11 H. So that would allow us to solve for HD, right, as a function of H. We'll see this in a minute with the example. But the physical elevation, like how high the spillway should be built, is often governed by how deep do you want the water level to be upstream, because there are going to be towns and buildings and farms in the river upstream of a dam. And oftentimes the dam is going to be lower. Having the flow over the front of the spillway is not a common event. This is a rare photo because they don't have water flowing over that dam every day. More of the time, they just have water going through internal pipes that you don't even see. So it's kind of an uncommon thing that there's so much water behind the dam that they need to release some of it over the spillway. Because when you release the water over the spillway, you're not capturing any of the electricity that could be generated. So I mean, that's one reason why you don't just always allow the water over the spillways. To have that water spinning a turbine and generating electricity, the flow has to be going through a tube that the impeller is inside of. So those little blades that get pushed by the flowing water don't spin when the water is falling down the front face of the dam. So this is a rare picture, and it's only occasionally that it's been so rainy in the watershed upstream that the water levels are at this design depth. So the height of the spillway crest is what dictates how high the water level is going to be upstream. So you may know the base elevation of buildings and farms, and there may be other canals or hydraulic structures upstream that you don't want to submerge. And so then that would govern what elevation you put the spillway crest at. Okay, So here, this equation in British gravitational units, we would have a different coefficient at the beginning if we were using SI units. But the length as units of feet and the height of the water above the Sharp-Crested Weir or above the physical height of the spillway crest, that height is also in feet. All right, so just to get a feel for how this equation works, we're going to say that we do know the elevation of some structure upstream, that we want the water level no deeper than 4350, and that would be the elevation above sea level. So if the water level should not exceed 4350, then what we're trying to figure out is what elevation should the spillway crest be built at. And we know what our anticipated maximum flow over that spillway is going to be. So we want to pick the elevation for the spillway so that it can pass 38,000 CFS. So if there's 38,000 CFS, there's going to be a certain height above the spillway. Now it may be that this is for the 100-year storm. So what if the 1,000-year storm comes around and there's 45,000 CFS? That just means that the water level would be even higher. But our analysis for purposes of this example is just figuring out what elevation should the spillway crest be at if we have this 38,000 CFS. So here's our formula. You know Q. L is the length of the spillway. So here it says it's 300 feet long. That length that it's talking about is this length, the lateral length that the water is flowing over. Okay, so that's the L. Essentially what we're doing in this example is you're solving for HD in order to find the elevation the spillway crest should be built. All right, so let me pause for a moment. I'll put you into the breakout groups. We're not especially pressured for time today, so we can afford to give you the time to actually calculate through this, check answers amongst yourselves. Let me put you into breakout groups 3. All right, so let's take a look at the solution to this one. It's not rocket surgery, as they say. All right, so we can just rearrange the spillway equation to solve for H sub D, because we know what flow rate is going to be passing over there. We know the length of the spillway. We just want to know how high is the water going to be backing up over that obstacle. A dam is an obstacle. The water is going to back up above it to have enough energy to get up over the obstacle. So 10.06 feet is H sub D. And so this is asking what elevation should it be built at. So if the water level is at 4350, then that means the spillway crest should be 4350 minus H sub D. Okay, so that means we should build the spillway at 4339.94 feet of elevation. All right, well there we have it, spillway. Let's talk a little bit more about weirs. Sadly, because this course is virtual this semester, it's not possible for us to go down into the lab. If it was, and part of the reason why we're going to finish early today is because we can't go down into the lab to actually watch a Broad-Crested Weir. In a normal semester, we'd go down to the lab for a few minutes of demo. But let me just show a couple of pictures and describe what's happening. You remember that we were talking about specific energy in the past week and a half, and that how when an obstruction is in the channel, this is a channel, it's clear, so there's glass on the back side, glass on the front side, and water is flowing from the left towards the right. So as the water, before this obstacle was there, just the water was flowing at some depth along the channel, but when the obstacle was put in place, the water level was rising upstream, and then it finally comes into equilibrium again when it doesn't have to rise any longer. I mean, at first it was rising because there was this barrier in the way. You know, the flow depth was a couple of inches, and the barrier is much taller than that. You can see they've got kind of a strip of putty along the side here, so it's a watertight seal. And so the water couldn't flow through the obstacle, so it had to pool. It had to, the water depth accumulated in was greater than out for this period of time while the pooling occurred. But then equilibrium is in equals out, and eventually it comes to a point to where the flow over the obstruction is the same as the flow coming towards the obstruction. So that equilibrium occurs when there was finally enough pooling upstream that the water could flow at the critical depth over the obstruction. Now, if you look, this is kind of tricky to know exactly which depth is the critical depth, because there's this drawdown portion as we have the water accelerating over the obstacle, and then there's this other drawdown portion where now you've got the water accelerating off the edge of the Broad-Crested Weir. So when I have been in our lab working with the Broad-Crested Weir that we have, what I've observed is that the critical depth is observed about halfway to 2/3 of the way along. And so I think that the critical depth would be right here at this location. And so there is a way with the equipment we have down in the lab to use a pin gauge and find out what is the depth of the flow above the obstruction, and with that y sub c you can find out what is the flow rate, because you know the flow per unit width and the relationship between y sub c and so on, and we can compare the known flow rate because we're using the hydraulic bench. Remember our stopwatch and dropping the plug method. So we can quantify the flow rate that is being pumped through this channel, find out how many liters per second it is, and then we can try and measure different depths and find out what would be the flow rate. And what I've just observed is that the critical depth is about 2/3 along the length. So what we're seeing here is flow at the minimum specific energy. We're observing that it achieves that critical depth, and then it flows at the critical depth briefly until then it flows over the edge again. It's more obvious, this flow rate's kind of high. If the flow rate is so that the gap here isn't so large, then it flows at the critical depth for longer. So a broad-crested weir is inducing critical flow over the obstruction. And the energy grade line, remember, is the depth plus some extra elevation above the flow depth associated with the kinetic energy. And so here's the velocity head. The velocity head is the distance from the water surface up to the energy grade line. And the energy grade line here is flat, because even though the depth decreases over the critical flow at the obstruction, the velocity was increasing. So in theory, we should have a flat energy grade line. In reality, the energy grade line is decreasing because there will be losses. But this is our broad-crested weir, and they work by inducing critical flow, and the function of a broad-crested weir is it's a tool you can use to regulate flow and also to measure the flow rate. And that's the main functionality of a broad-crested weir, is if you know it's forcing the critical depth and you measure the critical depth, if you know the width of the channel, you can use that to quantify Q. And it's not as easy as you might think. If you think about people who are irrigating crops, so you know, like a farmer, out west especially, in the western part of the United States, water is scarce. Not like here in the east where it's bountiful and oftentimes kind of a nuisance. In the west, farmers are allocated a certain amount of water, and there's a whole field of law, water law, that figures out how to settle disputes between landowners who have historical claims on limited quantities of water. And so these farmers who are irrigating water are only legally allowed to take a certain amount of water during a certain schedule each week, and it's on them to regulate the flow. And so to figure out how much flow is coming, they don't necessarily have like fancy magnetic flow meters. They're not dipping propeller-based velocity meters into the flow. What they'll do is they'll measure the depth over a hydraulic structure like a broad-crested weir. So the purpose of them is to measure flow. The disadvantage, though, of a broad-crested weir is you'll notice it has this step, and sediment and trash and debris, rocks, things can accumulate in the front face of this broad-crested weir. So they have some disadvantages. In a hydrology course that I occasionally get the opportunity to teach, we talk about other hydraulic structures that are used for quantifying flow. And there's a special flume called a partial flume, which is used to induce a hydraulic jump, and measuring different parameters of that hydraulic jump to quantify the flow rate Q. But this formula allows us to quantify what is the flow rate at a broad-crested weir when there is this notion of a discharge coefficient. You remember how I said this horizontal energy grade line is assuming that there's no energy loss because of the broad-crested weir? The reality is that there is energy loss, and so we have to take that into account if we're going to be using a structure like this to quantify the flow rate. And so you can estimate the coefficient of discharge by knowing the depth of the water, h, plus the velocity head. So h includes the depth of the water above the top of the weir. So in other words, y sub c plus the velocity head is h. Critical depth and the velocity head above the critical depth. And you remember what we said for a rectangular channel, that the overall specific energy is 3/2 of the critical depth. That's if it's a rectangular channel. Or a very wide channel. Remember that there's a technical definition for very wide. A channel that is 20 times wider than it is deep, we consider that a very wide channel, with air quotes around that. Very wide allows us to assume that regardless of the cross-sectional shape, it may be trapezoidal on the ends, but the end area is relatively insignificant if it's a very wide channel, and so that allows us to treat it like it is rectangular. So this equation works for rectangular or very wide channels. B is the width of the weir. Of course, G is the gravitational constant. C sub D, the discharge coefficient, has to do with energy loss. And you can calculate the discharge coefficient as shown. And then H would just be the height of the energy grade line above the top of the weir. And so H is a function of the critical depth. So we could just see how it says 2/3 of H. We could just put the critical depth in there, inside the parentheses. Now, this was a broad-crested weir. Here is a sharp-crested weir. And a sharp-crested weir is very similar to that spillway that we were just looking at, in the sense that there is some elevation datum, that crest, and we measure energy using that as the basis. And so here, location 1 is upstream far enough from the sharp-crested weir that the drawdown hasn't yet occurred, because there's some acceleration as the water approaches that overflow. It starts drawing down the depth. And so if we go a little bit further upstream to where it's a constant depth, so location 1, we can know both the depth of flow above the datum and the velocity head. And then at 2, the energy has been exchanged. TEL just stands for total energy line. It means the same thing as energy grade line. It is depth plus velocity head. So just look at between location 1 and location 2, what's happened to the energy. it's exchanged from a little bit of velocity and more depth, and then at location 2, all of the previous depth has been exchanged into additional velocity. So the velocity head at 2 is going to be larger than it was at 1 because of the acceleration that occurred as it approached that weir. So here's our specific energy equation, and we just say we want to compare the specific energy at 1 to the specific energy at 2, and 2 is at the datum. Y1 is 0. So we're saying that when the water gets down to the same height as the weir, then we could assume that Y1 is whatever its measurable depth is, Y2 is 0. So you can find the velocity over that sharp-crested weir by knowing the velocity at 1 and the depth at 1. So this is just rearranging the specific energy equation to solve for V2. In other words, if we know that Y1 incorporates both the, H incorporates the depth and the velocity head, then V2 is the square root of 2gh. And that should seem familiar to you if you remember the orifice equation, or when we solved for the Bernoulli equation with water coming out of a jet. The orifice equation told us you can measure the velocity of flow by the square root of 2gh, where h was the elevation of the center line of the opening up to the water level. So here, we're taking the velocity head into account as well, because it's not just water coming from a stationary tank, but it's water that has an approach velocity. So h includes its physical depth as well as the velocity head. So it's a function of the energy upstream. So that's the equation we can use for a sharp-crested weir. This is looking at a weir from the front. So this is a side view. This is a front view. And so L, the length of the weir, is, you can think of it as how wide the weir is. And some technical definitions here that it's in the textbook, but let me draw your attention to the difference between a suppressed weir and an unsuppressed weir. So a suppressed weir is one that is the full width of the channel. And it's called suppressed because of what happens to this nap. The nap is the water that's going over the edge. So if the water is going over the edge and the weir is the full width of the channel, there's some suction underneath the nap. Like, think about what happens when the water level is very low. It's just the trajectory of this jet is just going to like droop down pretty quick. But then as the velocity increases faster and faster, then, watch my hand on the picture, that nap kind of comes up a little bit and it creates a section of lower pressure under there. It's not necessarily ventilated to atmosphere. And so that interferes with the flow a little bit. And so this equation for a suppressed weir tries to take into account the fact that you may have negative atmospheric pressure underneath the flow that's going over the weir. Okay, so the coefficient of discharge, the C sub D, which we've talked about before, that accounts for energy loss, that is a function of how deep is the water, H, over the weir, relative to the height of the weir, Z. So we look at it from the side here. Here's Z. It's how tall is the sharp-crested weir, and then H is the height of the water up to the velocity head upstream before the drawdown occurs. So you can estimate the coefficient of discharge, and we can simplify that as long as the H to Z ratio is less than 2, and it's better to keep it less than 0.4 for real accuracy with this equation, but you can relate the height of the water and the flow rate using this equation, and this is very similar to what we saw with the spillway equation, for typical heights of water going over the edge, where we were modeling the spillway of a dam like a sharp-crested weir. So this formula will allow us to model a suppressed weir. Now, If you have the H to Z ratio really low, then the coefficient of discharge is about 0.62. So that's saying if H is small relative to Z, then the coefficient of discharge is just about 0.62. And so if you have 0.62 here, mix it with the 2/3, multiply that by the square root of 2g, so just combine all of these constants together, then here's the equation if you have a relatively low height of water going over the weir. So in British gravitational and SI units, what's the coefficient that combines together the square root of 2g, combines together the coefficient of discharge and the 2/3. So this is kind of like the bottom line for most flow conditions, unless the water is really deep before it flows over. In case there's a really big H, then you'd maybe need to calculate the flow condition appropriate C value. So the first one I showed you was a suppressed weir. This is an unsuppressed weir. And why it's called unsuppressed is that it allows air to get under the nap by only having the weir length being a portion of the channel width. So B is how wide the channel is, and the water is flowing over the weir at a length that's less than the width of the channel. So think of a rectangular channel that has a metal plate in it, and then this is all metal plate, and here's the width of the channel, but the water can only flow through this section that isn't as wide as the channel width. There are some approach losses. As the water is going over the edge, it has to kind of reestablish flow patterns. And so here, instead of the actual L, the physical length, you would have to calculate an L prime that takes into account ineffective flow area. So there's water that just kind of hangs out and isn't flowing over the weir at the edges because of contraction. All right, so that's all I have for you today. Before we part our ways 5 minutes early, let's take a look at the announcements. I think probably the main one to be aware of is that we've got an exam on Wednesday. Homework is due on Wednesday, and then phase 3 of the project due on Monday. All right, well, that's it for today, everybody. I hope you have a good one. Take care, and if you got any questions, send me an email or call me on Teams. Thank you. Bye-bye.